Hear me? All right, perfect. So yeah, my name is Jacob Silterra. I am a little bit of background about me. My background's actually in physics, and I moved into life sciences about 10 years ago and I got a master's in bioinformatics. Right now, my role is as a machine learning engineer at the Jameel Clinic of MIT. And what is that? Well, it was founded in 2018 with the goal by the Jameel Foundation, Community Jameel, and MIT, with the goal of advancing AI for health. A little bit more background. The use of AI in medicine has increased a lot, and I couldn't find anything more recent than 2020, which is a shame, but you can imagine that curve just continuing to go on. And something else is that it focuses, there's been a lot of activity in radiology specifically. 70% of these models are radiology. And you know, AI does very well with vision, and there's a lot of activity there. There's a lot of things like image segmentation, and it's very explainable and easy to use. So some of that is very easy to understand and has good uptake because they complement the doctor instead of replacing them. This one is a little bit strange. So these two models were developed at the Jameel Clinic. Mirai analyzes mammograms and predicts future breast cancer risk. Sybil analyzes low-dose CT scans, 3D images, and predicts future lung cancer risk. And again, reminder, early detection saves lives when it comes to cancer. So when a cancer is still localized, it has pretty good survival rate, especially for breast cancer, less for lung cancer, but I would rather have a 63% chance than a 7% chance. So the earlier we can detect things where the tumor is still contained, the better. All right, who here knows what a receiver operating curve is and what the AUC is? All right, this is a very common metric in binary classification. So the idea is, you know, whenever a lot of classifiers have a continuous spectrum from say 0 to 1. And often you need to separate, say, into low risk or high risk. So, and that's gonna trade off against false positives and false negatives. So what this does is plot the false positive rate on the x-axis and the true positive rate on the y-axis, and for a variety of different thresholds, sees where they are. So pure chance would be 0.5, just the diagonal line. Perfect would be 1.0. It would just be like a straight up and then straight over. No false positives, only true positives. And the AUC is the area under this curve. So it's a metric for classifiers. You don't have to pick a threshold yet. But just when we're comparing these different models, remember 0.5 is the bottom and 1.0 is perfect. The older model for breast cancer is something called the Tyrer-Cuzick, which just looks at a few risk factors: age, family history, some prior medical history, and physical characteristics. And it has an AUC of 0.63, which my opinion is about the minimum for something to be considered useful. It's not great, but it is better than nothing. Mirai is a little bit better than that. So this was published in 2020 by Adam Yala in the Barzilay group and validated in a larger study in 2020. Actually, I don't remember when that was published. Just a little bit of technical information on how it works. Really just encodes mammogram images. There's 4 standard views, typically, at least for 2D mammograms, which encoded by ResNet 18 and aggregated. One interesting thing that I thought was, at the beginning of this project, it was believed that risk factors would be helpful. But they are often absent as just a matter of practical reality. So doctors might like to plug those risk factors in addition to using the mammogram. But if they're not there, then it would still need to be able to work. So the model has an internal risk factor predictor. And if the doctor can input the risk factors, those are what's used. If not, then the model uses its own predictions. But it turns out that risk factors don't actually help with anything. So this was never used. Flowchart for the data set that was used to train Mirai. So the training data all came from MGH, about 50,000 patients and 200,000 exams. It was also tested on Karolinska, a data set from Karolinska in Sweden, and CGMH, Changdong Memorial Hospital in Taiwan. And the results, big win for Mirai. So again, Tyrer-Cuzick, the state of the art at the time, 0.63. And this group had published a previous model, image GL they called it, and 0.73 with Mirai being 0.77. And this is a prediction at 5 years out, by the way. It's much better at shorter time points. So what this does is predict risk at 1 year, 2 year, 3 year, 4 year, 5 year. And you can see the AUCs for these. I know, it's a little dense. But this was replicated at multiple sites all across the world. So we have, these are 5-year AUCs and certainly vary a little bit, but all very high. No, reasonably high. Something else to think about is bias, of course. There's, methods can be biased depending on training sets or whatever else. Something that does kind of bug me is people talk about this with AI a lot, as they should, but somehow always seem to forget that whatever AI is replacing has that problem as well. And so Tyrocusic, pretty bad when it comes to minorities, whereas Mirai is much better, much more consistent. So if you pick thresholds, if you start picking thresholds, this data, this is from an abstract, by the way. This study's coming out later this year. But if you look where Mirai and Tyrocusic disagree, and where Mirai is high and Tyrocusic is low, that's a cancer discovery rate of 20.8 per 1,000. Whereas for the other way around, Tyrocusic high, Mirai low, that's 1.9 per 1,000. So that difference of 19 per 1,000, that's the number of cancers discovered. Maybe that's a good place to pause and see if there's any questions. Yes?
The slide on the differences between minorities and white women.
Mm-hmm.
Any thoughts as to why the newer model is better than the older model with minorities? Or is that even a factor?
The older model, I think it was probably just designed, I'm not even sure if they used machine learning, it was more hand engineered and probably did this without really thinking about it.
It's not ML.
Yeah.
It's just like a couple of different factors.
Yeah, and so I think it's just having a much larger training set and make sure that diversity is represented. So obviously it's going to be different amounts, but as long as you have enough.
I just didn't know if there was a technical reason or just the fact that probably less minorities had mammograms than white folks.
I don't know. I mean, that would affect Mirai as well.
Yeah.
That issue would.
Okay.
Yeah.
So does it require any specific style of mammogram, or like multiple, like what kind of images does it accept?
So the question was, what kind of images does it accept? And the answer is, so 4 standard views is what it accepts. So left, right, top, side.
Okay, so that's mainly what is taken in most cases, right? Like almost any.
Yes, I think some of them are starting to do 3D. You can simulate these 2D from the 3D. All right, so moving on to Sybil, yes?
Is there any thought put into like false positive being like better than a false negative? Because in that way you like you see something that isn't there and you check further and there's no problem, but if there's a false negative, then you don't see it and then you find out about it later and sort of applications are lower. Is there any thought put into that?
Yes, there was a lot of thought put into that. This is the short answer. I mean, you might notice this high risk group is 20 per 1,000. That's 0.2%. It's not really the highest of risks, but because we are really interested in catching all possible cancers and tend to set the thresholds pretty low. Yes?
Well, before you go on, could you also talk about how it's used for planning the follow-ups? For like whether someone should get another mammogram in say 1 year, 2 years, 3 years, 4 years?
So I'm not a doctor. That's more of a decision for clinicians. Generally, the options are going to be that you either get enhanced screening now, so be sent to MRI, which is a more detailed type of exam, or be screened more frequently, or be more aggressive about reminding for follow-up. So if they were going to be screened only every 2 years, maybe they could be screened every year. Or I think some places are starting to introduce texting programs to remind people to go to their appointments, because a lot of people don't go to the doctor when they're not sick. Can't say as I blame them. But if they're at high risk, then it makes more sense.
Because that's sort of the main application of this, right?
Yeah,
It
absolutely.
doesn't actually detect the cancers. This is for when there's no visible cancer, and then you decide whether additional follow-ups are a good idea.
Yeah, absolutely. This is not for detecting current cancer. These rates would be pretty terrible. It's for future risk. Anybody else? All right. Right, so similar concept again. This time the training data was from the National Lung Cancer Screening Trial. So this was data from 2002 to 2004. Split up into training, validation, and test, as is usual. Also had test data sets from MGH and CGMH. In terms of technical architecture, pretty similar. This 3D ResNet, because we're dealing with 3D images. One interesting thing that I thought was worth calling out was guided attention. So here, a lot of these exams had a radiologist annotating regions of either precancerous nodules or cancerous nodules. And that was used as an attention layer during training to multiply the attention, to basically instruct the model to pay more attention to those regions. Good results. There isn't really a baseline of comparison as much for lung cancer, but I think these are pretty good. And consistent across these different data sets. So consistent across an LST, an MGH, and CGMH. Obviously, it drops a little bit over time. It's pretty good at predicting 1 to 2 years. I think 1 year might be something that a radiologist just missed. We're still having discussions about that. Predicting the future is hard, and the harder the further out you go. Deployment methods are, so we're a little bit more deliberate about deploying things. I'm not gonna beg you to use it right now, although you can. But when we deploy to a hospital, usually we do a retrospective analysis. So collect data that they have, run Mirai or Sybil on that data, validate that it works on that population, and select a threshold. So it's being used in, I think the total number of exams run through Mirai is now 1.7 million as of last count. A lot of these places are still doing the retrospective validation, but some, especially in the US, are using it prospectively. And Sybil's a little bit newer, so it hasn't had as much time to permeate through, but a lot of places are analyzing it for future use. It's open source. We at MIT like open things. You can download it from GitHub. Weights are all available. There's a Docker container available. If you're tech savvy, you can get this up and running in probably 15 minutes. And thank you very much. I think we've got good question time yet.
Yeah, I'm just curious what drives the differences in adoption